Hello and welcome to week 2, day 2 of Lab 1102. We're going to talk today a little bit about. Okay, sorry, I needed to pause and get my slide pane back. We're going to talk a little bit today about basic analytical lab equipment. So I'm going to start by opening this Word document that I have uploaded on Blackboard that just has some links to some basic lab equipment at a chemical and lab equipment supply place. So we've got some pictures to show to talk about. Ordinarily, I would pull some of these out of the storeroom to show you so we could and maybe pass them around so you could gain a little bit more physical familiarity. Uh, but this is what we have. So if we just bear with things for a moment while the browser opens. Go ahead and hit pause so you don't have to wait for that. Okay, I have the web pages open now. Wanted to start by showing you a desiccator. Frequently, when you're measuring chemicals or dealing with plant-based samples, you need to dry them. A lot of chemicals will hold on to water molecules, and that needs to be removed before you can get an accurate weight of how much of the chemical you're interested in there is. A lot of times you care about how much water there is in a plant-based sample. So you'll put them in an oven for overnight. Tends to work on an oven just slightly above. At the pulp mill, we used 105 degrees C. That seems to be about normal. The specific temperature will usually be defined in a standard related to your industry. Cannabis being a fairly new industry is likely to be borrowing a standard from someone else. I suspect it's going to be around 105 degrees C. So you'll dry the sample in an oven and stick it in a desiccator. This one happens to be a glass one. They also have plastic ones. The lid here is usually you've got a layer of silicon-based grease in between the lid and the main body. That lip there is probably about an inch and a half wide, so it's a nice thick thing. So no air should flow through that. Uh, if you note, there is a picture of one of these in the textbook. There's usually some sort of tray right there at about that lip there. And then the bottom here is filled with a desiccant. It's a material that will absorb water very quickly. So once the air in here is dry, all the water will get absorbed into the desiccant. Hopefully it grabs things faster than anything you stick in it. Um, so most desiccants are reusable. You have to stick them in an oven and dry them, and then you can reuse them. They tend to change color as they absorb more water. That way you've got an indication of how much life is left in your desiccant before you need to recharge it. The ones I remember using most at the pulp mill started out a fairly bright blue, and then as they absorbed water, they turned sort of a purplish pinkish. And once it was mostly that color, we'd put it in the oven, dry it out, and then reuse it. So the thing about this is you're sticking something hot in, so it's gonna, you know, things expand as they heat up. So you stick some hot things in, and as you're putting the lid back on, it's probably letting some air out. And as everything cools back down, it will end up getting kind of a bit of a vacuum in there. So you can't just pull the lid off between the grease and the bit of vacuum you've likely developed. It's not going to want to just come off. So you've got to kind of rotate it and slide it and just break that vacuum before you can get it off. Some of them have a valve here, so you can crack that open and break the vacuum to get the lid off. But that's what a desiccator is. Basically, it's just a piece of glassware that allows you to store a dried sample and not have it reabsorb water from the environment. All right, so next we'll talk about burettes. These are very thin, graduated pieces of glassware. Let's see if I can zoom in a bit. So you can see it's got markings here. These tend to be every 1 milliliter with smaller markings. You can kind of see the smaller markings for usually for tenths of a milliliter. And it's got a valve at the bottom, so you stick these on a stand, and then they're used mostly for titrations. So you let out small amounts until the color or pH or whatever you're expecting to happen in the solution under it occurs. Then you stop, and if you've noted the volume where it started and the volume where it finished, you know how much chemical you added fairly precisely. One thing I do want you to note is this phrase right here: they are calibrated to deliver. And we'll talk a little bit about calibrated to contain versus calibrated to deliver in a minute. It's an important phrase when you're dealing with volumetric glassware. So you can see they come in different capacities. The ones I used to use most often at the pulp mill were 100 milliliters. The smallest graduation lines were 0.2 milliliters. It claimed an accuracy tolerance of plus or minus 0.1 milliliter. You can see they're not exactly the cheapest thing out there, but none of the precise calibrated volumetric glassware really is going to be. All right, let's talk a bit about graduated cylinders. These ones happen to be calibrated to deliver. We'll talk when we get to pipettes. We'll talk more about to deliver pipettes and volumetric cylinders. So, kind of like the burette, this is a tall, fairly thin cylinder with markings on the side at different volumes. This happens to be a 250 milliliter one with major lines every 10 milliliters, and if I scroll down I can see what the minor ones are, every 2 milliliters. One of the things to note about these is there's a little gap between the bottom and where the markings start. So like the 10 milliliter one, you can't measure less than 1 milliliter on because there's no markings down there. 25 milliliter one starts at 3. Do they give tolerances on the? They don't give the tolerance on this one. Tolerances on these tend to be less precise. The burettes, so that 100 milliliter burette is maybe a centimeter in diameter and on the order of 3 feet long. They're not small, so but that lets you get more graduations and a bit more accuracy that way. So beakers, and we've probably all seen beakers. They look like that. We've got a sort of graduation scale on the side there. Those are not very precise at all. You don't want to use those for anything that you need anything more than just kind of a ballpark measurement. So if you look, I can see that that's going to be about 45. That's about 40. You'll note they're usually labeled approximate volume. They're not intended to be used for measuring. All right, volumetric flask. Volumetric flask is a round bottom flask like so. This one's a 500 milliliter flask. You can only barely see it, but right here there's a thin line etched into the glass. So if you get water right at the level of that line, it should be exactly 500 milliliters within the calibration limits of the glassware. They usually come with this one has a plastic stopper, but frequently it's a ground glass stopper. So you have a glass tape at a specific taper on the top and a matching glass plug with the exact same taper on the plug. These ones are calibrated to contain instead of to deliver. So to deliver, it is calibrated, the calibration's adjusted so that once you pour it out, there's going to be a couple drops left in the bottom. That's just the nature of how things work. There's always going to be a couple drops left in until things air dry. Calibrated to deliver means they've adjusted for those couple of drops that are left out. So in the graduated cylinders, if I measure 10 milliliters and I pour it out, I'm going to pour out 10 milliliters and I don't need to worry about those couple of drops that are in the bottom. Volumetric flasks are calibrated to contain. So if I were to pour this out, those couple of drops in the bottom, I would need to somehow include in order to get the 500 milliliters. Frequently, we use volumetric flasks to, we'll be mixing something, and I want it mixed and diluted to that particular volume, and then maybe I don't need to use that entire volume for the next step. In which case I'm just fine. I don't care how much is left in after I pour it out because I'm not using that volume again. Or if I am, I'm diluting it further so I can rinse it out real well, and so I made sure I've moved all the material out of it. Volumetric pipettes. Also, they look like a piece of glass tubing with a wide spot in it. This one appears to be 6 milliliters. So if you probably can't see it, but somewhere in here there is going to be a line just like there was on the volumetric cylinder. If you fill that pipette to exactly to that line, it contains 6 milliliters plus or minus. Okay, so see if we can find the 6 milliliter one. 6 milliliters plus or minus 0.01 milliliters. They're for fairly precise measurements. You don't have a lot of adjustment. You've got half milliliter, 1 milliliter, 2 milliliters. You're limited by that. They are, there it is, to deliver. They are calibrated to deliver. So once I forgot to search for pipette bulb, just a moment. Bulbs. So you stick a bulb on the end of this. Let me show you what one of those. You stick a bulb on the end of this. You squeeze the air out of it, and you let the suction from that pull the liquid up. Once you have the liquid at the set amount, and we will have to practice this in the lab or see what the videos are. There's a few different styles of bulb. They all work. and they take slightly different techniques and some practice. So hopefully we get some lab time and you can practice this. But once you filled it to the right level, you pull the bulb off the top. Whatever you've pulled into it drains out. There's going to be a couple of drops left in the bottom. It is calibrated to deliver. Do not blow those drops out. That will throw off your measurement. Those drops are meant to stay there. You can take it over a waste container and blow the liquid out there. That's fine, but do not force that liquid into that liquid is not part of your measurement. Apparently I opened that one twice. Microbalances. I'm missing the pipettes. Just a moment. No? I'm not. Apparently I got the wrong... Okay. There we go. So we do also have what's called pipetters. This is not the best view of them here. So that'll work. These are adjustable in volume. You depress the plunger here, and as you let it up, it sucks liquid up into a disposable tip that attaches down here. You can adjust the volume turning this knob. There's a readout here that tells you how much you've got. They are available in ranges 0.2 to 2 microliters. So remember, metric system micro is 10 to the minus 6th, milli is 10 to the minus 3rd, so there are 1,000 microliters in each milliliter. So these are capable of some very, very tiny measurements. We're talking sub-drop of water size, and a lot of times you have a difficulty getting the drop off the tip of the pipetter. That can be a problem with some very small measurements. So there's a different physical device for each range. They take slightly different size tips. This one goes from 1 to 10 milliliters, so it's adjustable. So this lets you get the oddball measurements that you wouldn't be able to do with glass pipettes. They're also tend to be a little bit easier to use. Finally, let's talk about electric microbalances. This isn't the exact model we have in the lab, although that is a similar range. We can go up to about 50 grams on those. Get down to usually, different ones have different readability. So this is micrograms. So that is 1,000th of a milligram. So 5 micrograms. It might be 1 or 2. I believe that's one decimal place farther out than the ones in the lab have. So I believe we've got four decimal places on ours in the lab. You've got a little tray that sits on top of the balance mechanism that can be pulled off and cleaned. The whole thing is inside an air shield because they are sensitive enough that air movement can mess things up a little bit. So you've got these doors on each side and the top that you can open to get the sample in, close to get your measurements. If you need to put something on. So in a lot of situations, most situations where you're using one, you're going to be, measuring stuff into some sort of container. So there's little plastic weigh boats or weighing papers. You kind of fold the weighing paper a little bit to make it kind of boat-like. Um, but you put that on, you get the weight of that, and back in the day, you'd have to write down that weight and then subtract it from your final one. On these, you can usually press the tare button, and so it says, okay, I'll just ignore that and call it 0. Then you put what you need to weigh into it, and you're weighing that, and it's doing the subtraction automatically. Again, with some lab time, we will get a chance to use all of these. Okay, so let us move along. All right, let's talk about preparing solutions. This is the other situation that has calculations that you really should know. And in thinking about it a bit more, both types of calculations that fall under this are really, it's the same calculation underlaying everything. So a lot of times you'll be making stock solutions or taking a stock solution and diluting it to what you need it to be at. And so you'll need to, you're doing a dilution where you need to know what the concentration is, accurately know what the concentration is in the diluted solution. Your concentrated start point may be a concentrated solution, or it may be a solid. Either way works. So let's go here. I've got my notes on this that I've uploaded. So really the key detail for this, zoom in a bit, oh, that's too far. The key detail for this is that the amount of solutes is going to be the same. The amount of solute in your diluted solution is going to be the same as the amount that was in however much of your concentrated stuff you used to make that diluted solution. We can really do this in either moles or mass. Moles is probably the better choice, especially if you might be dealing with any reactions. We shouldn't be dealing with any reactions, so mass works reasonably well as well. Volume is a bad choice because it's dependent on temperature. So if we are making 1 liter of a 2 molar solution, for example, there will be 2 moles of solute in that solution we're making, and so we need 2 moles of solute in however much of the concentrated form we're using. So step by step, the first step is to figure out how much solute do we need to have in our diluted solution. So, for example, how much, if we're making a sodium hydroxide solution, and we need to make a 5 liters of a 1 molar sodium hydroxide solution because we're going to need a lot of it at that concentration. A lot of time you can get sodium hydroxide in pellet form, so we've got solid sodium hydroxide pellets. They're essentially pure. How much do we need to weigh out to make our 5 liters? So we have 5 liters. We need it to be at 1 mole per liter. Liters will cancel out here, so leaving just moles. We'll need 5 moles of sodium hydroxide. The next step is to see how much of the concentrated form we need to do that. So in this case, we're dealing with solid sodium hydroxide. We need 5 moles. Sodium hydroxide has a molecular weight of 40, so it's 23. It's just showing how I came up with 40. 16 is the molecular weight of oxygen. 1 is the molecular weight for hydrogen. 23 is the molecular weight for sodium. So we've got 5 moles times 40 grams per mole. We have 200 grams of sodium hydroxide we need. We can measure out 200 grams, mix it with our 5 liters, and we've got our solution. We don't have to start with the powder. We could start with another solution and make a more dilute one. So concentrated sulfuric acid is frequently sold in at 98%, which is 18 molar. How much 18 molar sodium hydroxide do we need to make 1 liter of 0.1 molar sodium hydroxide? And I purposefully went for a large difference because I thought it might be big enough we need to do serial dilutions. And I probably would. So what can happen in a situation like this is sometimes you can't get a good measurement. You can't easily measure the small amount you need. And the very concentrated ones tend to be, they're kind of dangerous. Maybe you don't want to risk sucking some into your pipetter and corroding the insides of it. So you want to, sometimes you'll do this in steps. So, dilute it to a 5 molar solution, and then dilute the 5 molar solution to a 1 molar solution, and dilute some of that to a 0.1 molar solution. So you've got a series of steps, and at each step, it's going to be the same calculation. Those of you who are in chemistry right now probably have seen this as this volume 1 times concentration 1 equals volume 2 times concentration 2. So, volume times concentration, when you're dealing with, especially with molarity, you've got amount of solute in your concentrated form is amount of solute in your diluted form. That's all it is. It's the same concentration or same calculation I've been talking about. So we can do that to go from whatever the concentrated version is to the first dilution, and then from the first dilution to the second dilution, and then the second dilution to the next one until we get to whatever our final concentration is. So, first step, how many moles of sodium sulfuric acid do I need in my 1 liter of 0.1 molar final solution? So I've got 1 liter. 0.1 molar is 0.1 moles per liter, so I need 0.1 moles of sodium sulfuric acid. Sorry. Next step is to see what volume of 18 molar sulfuric acid that needs to be. So I've got, I know I need 0.1 moles. 18 moles is 18 moles per liter, so I'm going to divide by 18 moles per liter of concentrated sulfuric acid. So my moles cancel, and I have 0.1 divided by 18 is equal to 0.00555555, repeating liters of sulfuric acid. That is not a very useful measurement in terms of actually being able to do something with it. So I divide it by 1,000 to get into milliliters, 1,000 milliliters per liter. So 5.55 repeating milliliters of sulfuric acid. At some point I'm going to have to round that. I did not go back 5 liters, so that should be one significant figure. Yeah. So there we go. And the calculations are pretty much that simple. I may need to do some, as I did here, another step to get it from whatever units I come out with to a unit that's convenient for measurement. If this is smaller, I might have needed to go to microliters. If I was making more of this, I might have needed to switch to kilograms, just to make it a more convenient, put the number in a more convenient range for measuring. You know, I'm not going to find something that measures this small that's calibrated in liters, so I need to convert it to milliliters to find equipment that will work. Okay, back to this. All right, so let's talk for a minute about software. In terms of software, aside from whatever specialty software runs the instrument you're using, um, usually you're going to use it for statistics and graphing, really. It's also some amount of just data storage, but the software you'd use for statistics and graphing will kind of have that built in. So Excel is always an option or something similar. Excel, OpenOffice, Google Office. Um, I like to make sure I always know how to do something in Excel and not necessarily rely on something else, because no matter where I go, I always will have access to a spreadsheet of some sort. Um, it would be fairly difficult in this day and age to find a situation where you had access to a computer and not a spreadsheet. Um, so knowing how to do it in Excel is worthwhile. There's other options like MATLAB, Mathematica, MathCAD, things like that. You can do the statistics in, you can do the graphing in. They do a wonderful job, but the company has to pay for them. Granted, they have to pay for Excel too, but it's usually bundled with other things they need, like the word processor. We've got other options such as R, which is essentially an open source language specific for math and statistics. I know that's not quite exactly right, but it's kind of what it is. Um, there are other options along that line. You could probably use Python instead. There is an open source clone of MATLAB called Octave that would probably work. You've also got specialty software packages such as SPSS, Minitab, things like that. Any of those would work as well. It all depends on what you've got available. Again, you will almost always have a spreadsheet available. You may or may not have permission and rights to install something like R or Octave or OpenOffice for that matter, on the computer you've got at work, so that may not be an option. Something like Excel usually is. Um, for things like this, as much as I do like open source software where possible, um, I, however, I've never been able to really embrace using OpenOffice or LibreOffice widely because they don't have the statistics. Um, yes, they can do averages and standard deviations and such, but when you get into some of the more advanced statistics, analysis of variance and things, that's built into Excel, and it's not built into OpenOffice. Or at least it wasn't last time I looked. So that's just something to keep in mind. You've got quite possibly more options now than you will have later on, but you might not have those same options later. So be flexible and maybe try things a few ways so you know how to work around not having the tools you're used to. The last thing I wanted to talk about today is lab notebooks. This is basically a formal record of what you did, how you did it, what the results are. Usually there's some space for analysis. I know there are some electronic lab notebook programs out there. I've not had the opportunity to play with them. One of the important things to know about lab notebooks is they can be a legal document. The text mentions that they could be proof for patent and intellectual property issues. in some instances, they are also, you know, meant to be evidence that you followed the method you said you would follow. You know, it's a document you've signed that said, I followed this method on this day, and this is it. It's important to take notes in them, make note of anything that went wrong, make note of anything you needed to rerun. Um, document everything. That way, if somebody comes back and says your cannabis was contaminated because you didn't do things right, you can say, no, I did it this way and this way and this way and this way, exactly as I was supposed to. It can be a legal document for that reason. That's it for what I had today.